Hey everyone, Rufa here. So today we are going to jump back into 2D kinematics or linear kinematics. And so this would be stuff like projectile motion, the motion of throwing things and cannonballs and jumping and falling, all sorts of stuff like that. So first we're going to talk about relative speed and velocity. These are your classic train and boat problems that are pretty common in physics. So say you're sitting at your table or sitting on your bed at home, you're taking notes. What's your velocity? Well, you're just sitting there, so you might say that your velocity is 0. However, you are also rotating on Earth at around 1100 kilometers per hour. You're also orbiting the sun at 108,000 kilometers per hour. And you're moving through the Milky Way galaxy at 720,000 kilometers per hour. So what's your velocity? Is it 0? Is it 720,000 kilometers per hour? Huh. Well, it's all relative, man. In order to describe motion, you need a frame of reference. So a frame of reference is a defined set of boundaries against which we measure the motion of an object. The motion of an object is relative to many different frames of reference. So in the example above, your velocity with respect to the room, what do you think it is? Well, with respect to your room, you're not moving. You're just sitting on your bed or you're sitting at your desk. So your velocity is 0 with respect to the room. With respect to Earth's axis, well, Earth's rotating about 1100 kilometers per hour about its axis. So with respect to Earth's axis, you're moving 1100 kilometers per hour. With respect to the sun, 108,000 kilometers per hour. And with respect to the center of the Milky Way galaxy, 720,000 kilometers per hour. So again, you need a reference frame in order to really say how an object is moving, what its motion is. This Mythbusters trick shot video, I recommend that you watch it on your own. I'm going to put it on without any sound if I can here.
Very close to
Oh, it's going to show sound. All right. Let's refresh this. Let me find a spot here. Okay, so in this video, what they do is they are launching a cannonball from the back of a truck. And they're trying to launch it at the same exact speed that the truck is going. And they've got somebody observing from the truck and someone observing from the ground, like you see right here. So I want you to watch this video before you continue with my video, just to see what's happening in the clip. So with respect to the ground, how is this ball moving? Well, with respect to the ground, this ball is just falling straight down. So this observer on the ground is just seeing the ball fall straight down. Okay? So that means in the x direction, it has no velocity with respect to the ground. So with respect to the ground, Vx for this ball is 0. Now, if we're thinking about the truck, and we're an observer, this person, or an observer on the truck, watching this happen. The truck is moving this way, the ball is getting shot out of the cannon this way, and so from the truck's point of view, the truck is moving along this path, it's moving away from the ball. So the velocity of the ball with respect to the truck is going to be not 0, it's going to be something, not 0, okay? So that can be kind of tricky to think about. How can something have a velocity in one reference frame but not in another? Well, again, that's because motion is relative, and this truck is moving, okay? We'll do some examples to make this a little more clear. So, first problem we have here. A person walks to the right with a velocity of 2 meters per second on a platform that moves with a velocity of 1 meter per second to the right. What is the person's velocity relative to the platform? So our reference frame is the platform. And what we need to do is we need to just look at the things that are moving on the platform. We don't need to think about what the platform is doing. We're looking at things on the platform. It's like you in your room. We're not looking at what your room is doing, how it's rotating around the earth. We're just looking at you sitting in your room. So with respect to the platform, this person's velocity is just 2 meters per second. Now, what is the person's velocity relative to the ground? So relative to the ground, we got to think about all the things that are moving on top of the ground and above it. So reference frame is ground. Okay. You write that U better. So what we need to do is we need to think about the vectors that are in this problem. We have 2 meters per second and we have 1 meter per second. They're going in the same direction, so we can add them together. So the velocity of the platform is 1 and the velocity of the person is 2. So to somebody on the ground watching this, they would see the person going 3 meters per second because we're adding those vectors together. Okay, so we're going to do some more examples, some more complicated ones to help you out here. Looking at practice 2, I want you to try this on your own before you watch the solution. So try it on your own first, please. You can throw a pie at 32 meters per second. If you are standing on a train traveling 32 meters per second east and throw a pie forward, which is the direction east, what is its resultant or its total velocity? So you and your pie, you're throwing your pie at 32 meters per second. The train is moving 32 meters per second. They're both moving in the same direction, so we can add these vectors together. So we have v pi plus v train, oops, not p train, v train. So we've got v pi plus v train, and that's going to give us our resultant. So 32 plus 32 is 64. So we have 64 meters per second, but we can't just leave that value there. Remember, these are vectors, and you add a vector to a vector, and you're going to get another vector. So what else do we need? We need a direction. So it's 64 meters per second east is the direction that this train is going. Nope, nope, don't want that. Don't want that. Let's bring this back here. Okay, so 32 meters per second east. I'll clear that out. And again, with these, we're just adding vectors. That's all we're really doing. We're just playing around with vectors. So next problem, I want you to practice this on your own before, and pause the video before listening for the solution. So a bowling team on a train heads east at 15 meters per second. A stationary observer watches them play as they pass. At what velocity would the following throws appear to be moving at? So here's a train. Train is moving at 15 meters per second east. And we've got Cameron, who throws 12 meters per second east. And let's just take this one at a time. So both of these vectors are going in the same direction. That means we have 12 plus 15. So to a ground observer, a stationary observer, this is going to appear to be moving at 27 meters per second east because we're just taking 12 plus 15. Okay, I'm going to erase that 12 here. Next, we have Hannah. Hannah is throwing at 18 meters per second to the east. Okay, so again, these vectors are going in the same direction. We can add them up. So we have 18 plus 15. So we get 33 meters per second. And again, direction to the east. Next, we have Ralphie. Ralphie throws his bowling ball in a different direction. Ralphie's throwing his bowling ball at 15 meters per second to the west. Again, it's a good idea to draw pictures for these guys, so make sure that you're trying to draw some pictures. Hopefully they're better than mine. So Ralphie's throwing 15 meters per second to the west. So we have to add these vectors. And remember that if a vector is going in the other direction, we can subtract it. So we have the train velocity, 15 meters per second to the east. We're subtracting Ralphie's, 15 meters per second to the west. That gives us 0. So Ralphie's throw appears to not be moving at all to the stationary observer. So if you were watching this train and Ralphie throws his bowling ball, you would just see the bowling ball stay where it was. Maybe it would go straight down, but its x velocity would be 0. Okay. So I do have a couple other practice problems. If you do want to try them, some classic train problems, they are on my Google Slides and Google Classroom. But again, I'm not super worried that you know how to do these. The first one, please give it a try though. Okay, so homework is in the Giancoli book. These are posted to Google Classroom. And there's an answer key posted as well, because again, I'm concerned about you showing work and learning the process rather than just putting in the answers. So you will get points if you show your work and show your process. You will not get points for just writing down the answer key because it's already here. All right, so that's all I have for you for relative motion. Next time we're going to talk about the independence of perpendicular vectors.